Welcome back to Boring Science for Sleep, where the most extraordinary mysteries of the universe become gentle whispers that guide you toward peaceful rest. I'm so glad you've chosen to spend this quiet time exploring the cosmos with me tonight. Before we begin our journey into one of the most mind-bending questions in modern physics, I'd love to hear from you. Have you ever stared into a starry night sky and wondered if what you're seeing is real, or if perhaps you're looking at something far stranger than you could imagine? Share your thoughts in the comments below. I read every single one, and your curiosity always inspires the next adventure we'll take together. Tonight, we're going to explore a question that might sound like science fiction, but is grounded in some of the most cutting-edge theoretical physics of our time. Could our entire universe, everything we see, touch, and experience, actually exist within the event horizon of a massive black hole? As you settle into your comfortable space, perhaps adjusting your pillow or pulling a soft blanket a little closer, imagine yourself floating weightlessly in the vastness of space. The temperature around you is perfectly comfortable, neither warm nor cool, and there's a gentle, almost imperceptible hum of the cosmic background radiation that fills all of space like a lullaby from the birth of time itself. Picture, if you will, the moment just before dawn in a quiet observatory nestled high in the mountains of Chile, where the air is so clear and still that every star seems to pulse with its own gentle heartbeat. The Atacama Desert stretches endlessly below, its ancient landscape sculpted by wind and time into patterns that mirror the cosmic structures astronomers study through their telescopes. The observatory dome stands silhouetted against a sky painted with more stars than you could count in a lifetime, each one a distant sun carrying its own collection of worlds, its own stories written in the language of nuclear fire and gravitational dance. Dr. Elena Rodriguez sits at her mahogany desk, surrounded by printouts covered in elegant mathematical equations that flow across the pages like poetry written in symbols. Her coffee has long since grown cold in its ceramic mug, forgotten as she contemplates numbers that describe the very fabric of reality itself. The gentle hum of computers processing astronomical data creates a soothing white noise that mingles with the distant sound of wind moving through the valley below. For months, she's been working on calculations that seem to suggest something impossible, that the boundary of our observable universe shares remarkable similarities with the event horizon of a black hole so massive it defies human imagination. The night air carries the faint scent of mountain wildflowers and the crisp, clean smell of thin atmosphere at high altitude. In the distance, the gentle rustle of wind moving through ancient pine trees creates a natural symphony that has played for thousands of years, unchanged by the cosmic revelations being discovered in the observatory's quiet halls. But Elena's attention is focused on something far more profound and distant, the possibility that everything she has ever known, every galaxy visible through the world's most powerful telescopes, every particle of matter and every quantum of energy exists within a cosmic structure so vast and unified that it challenges our deepest assumptions about the nature of existence itself. Above her, the Milky Way stretches across the sky like a river of light, its spiral arms containing hundreds of billions of stars, each one potentially warming planets where life might have emerged and evolved. The center of our galaxy glows with a soft luminescence, hiding within its heart a supermassive black hole millions of times more massive than our Sun, quietly anchoring the gravitational dance of our entire stellar neighbourhood. Yet even this cosmic giant pales in comparison to the theoretical structure Elena contemplates. A black hole so enormous that it could contain not just our galaxy, but every galaxy we've ever observed, every cluster and supercluster of galaxies stretching across billions of light years of space. Black holes have long captured our imagination as cosmic monsters, devouring everything that ventures too close, warping space and time around them like whirlpools in the fabric of reality itself. These enigmatic objects, born from the gravitational collapse of massive stars when they exhaust their nuclear fuel and can no longer support themselves against their own gravity, create regions where the normal rules of physics bend and twist in ways that challenge our understanding of the cosmos. When a star at least 25 times more massive than our Sun reaches the end of its life, not even the pressure of neutrons can halt its gravitational collapse, and it becomes a black hole, a region where space-time curves so severely that it forms a cosmic trap from which nothing can ever escape. But what if these mysterious entities aren't separate from us at all? What if instead of being distant objects to observe and study from afar, we find ourselves intimately connected to them in ways we never imagined? This question emerged not from wild speculation or science fiction, but from the careful mathematical work of theoretical physicists who noticed something curious and beautiful about the numbers that describe our universe. In research institutes and universities around the world, scientists began to notice striking similarities between certain properties of black holes and fundamental characteristics of our observable universe. Connections so precise they seem to transcend mere coincidence. Like pieces of a vast cosmic puzzle slowly falling into place over decades of careful research, these connections suggested a possibility so extraordinary that it required them to completely reimagine our place in the cosmic order. The observable universe, that sphere of space approximately 93 billion light-years in diameter, from which light has had enough time to reach us since the Big Bang occurred 13.8 billion years ago, shares mathematical properties with black hole event horizons that appear too precise and elegant to be mere accidents of cosmic architecture. As Eleanor reviews her calculations one more time, watching the eastern sky slowly lighten with the first hints of dawn, she marvels at the elegant beauty of the equations that describe how mass, energy, space, and time interweave to create the cosmic tapestry we call home. The mathematics speaks of unity and connection, of deep underlying principles that link the smallest quantum fluctuations to the largest cosmic structures, suggesting a universe that might be far more coherent, purposeful, and unified than anyone had previously dared to imagine. To understand how we might be living inside a black hole, we must first gently explore what a black hole truly is, beyond the dramatic imagery of science fiction films and the sensationalized descriptions that often accompany popular accounts of these cosmic phenomena. Imagine a region of space where gravity has become so extraordinarily intense that it warps the very fabric of space-time into a steep, inescapable gravitational well, curving the geometry of reality itself in ways that create a kind of cosmic trap from which nothing, not matter, not energy, not even light travelling at the universe's ultimate speed limit, can ever return to the outside world. Picture a vast rubber sheet stretched perfectly flat and smooth, representing the normal, undisturbed geometry of empty spacetime, where no matter or energy is present to create gravitational fields. Now imagine placing a bowling ball at the center of this sheet, watching as its weight creates a deep circular depression that curves the entire surface around it, with the curvature becoming more pronounced the closer you get to the ball itself. This simple but profound analogy captures something essential about how mass and energy curve the geometry of spacetime according to Einstein's field equations, creating the gravitational effects we observe throughout the cosmos, from the gentle pull that keeps us anchored to Earth's surface to the vast gravitational fields that hold galaxies together across millions of light years. But near a black hole, this curvature becomes so extreme and pronounced that the rubber sheet analogy breaks down, forming what mathematicians call a trumpet shape, a surface that curves inward so steeply and dramatically that any path leading into the depression can never curve back out again, no matter how much energy or effort might be applied. The mathematics describing this extreme curvature reveals space-time geometry so warped that it creates what physicists call a trapped surface, where all possible paths through space and time lead inexorably inward toward the black hole's center, like water flowing into a drain from which no drop can ever return. The boundary around a black hole, known as the event horizon, represents a point of no return in the most absolute and fundamental sense possible in our universe. It's not a physical surface you could touch with your hand, like the rocky surface of a planet or the turbulent boundary of a star's atmosphere, but rather an invisible sphere in space defined by pure geometry, the mathematical boundary beyond which the curvature of space-time becomes so severe that all possible trajectories through space and time lead inexorably inward toward the central singularity. This boundary exists as a consequence of space-time geometry itself, determined entirely by the mass and energy contained within it according to principles that flow directly from Einstein's theory of general relativity. The size of this geometrical boundary depends entirely and precisely on the black hole's mass, following a mathematical relationship discovered by Carl Schwarzschild in 1916, just months after Einstein published his revolutionary theory describing gravity as space-time curvature. Schwarzschild, working in the trenches during World War I and tragically dying of illness shortly after making his discovery, found that the radius of a black hole's event horizon is directly proportional to its mass, with the constant of proportionality involving fundamental constants of nature, including the speed of light and Newton's gravitational constant. For a black hole with the mass of our Sun, about 2 × 1030 kilograms, a number so large it's difficult to comprehend, the event horizon would have a radius of only about 3 kilometers, smaller than most cities and roughly the size of a small mountain. Such a stellar mass black hole would be extraordinarily dense, containing more mass than our entire solar system's central star, compressed into a sphere smaller than Mount Everest. For a black hole with 1,000 times the mass of our Sun, the horizon would be about 3,000 kilometers across, roughly the size of a small moon. But for a black hole containing as much mass as all the stars, planets, dark matter, and energy in our observable universe, approximately 10⁻53 kilograms distributed across space, the event horizon would need to be approximately 46 billion light-years in radius, creating a sphere roughly 92 billion light-years in diameter. This is a distance so vast that light, travelling at 300,000 kilometers per second, would take over 90 billion years to cross from one side to the other, assuming it could somehow escape the black hole's gravitational grip. Here's where our story takes a fascinating and potentially revolutionary turn that has captivated theoretical physicists and cosmologists for decades. When astronomers carefully measure the size of our observable universe using the most sophisticated instruments and techniques available, the sphere of space from which light has had enough time to reach us since the Big Bang occurred approximately 13.8 billion years ago, they find that it is approximately 93 billion light-years in diameter. The remarkable correspondence between these two numbers isn't merely a curious coincidence that we can dismiss as an accident of cosmic architecture. It suggests a deep mathematical relationship with profound implications for our understanding of cosmic structure and the fundamental nature of reality itself. This isn't the only similarity. Our observable universe has a boundary that functions remarkably like an event horizon. Beyond this cosmic horizon, galaxies are receding so rapidly due to space's expansion that their light can never reach us, no matter how long we wait. Just as nothing can escape from within a black hole's event horizon, information from beyond our cosmic horizon can never reach us. The mathematics describing this cosmic boundary share elegant similarities with equations governing black hole event horizons. Both involve regions beyond which information cannot travel to reach an observer. Both are defined by the interplay of mass, space, and time, and both create fundamental limits on what can be known or observed. The Schwarzschild radius defining a black hole's event horizon and the Hubble radius defining our observable universe's edge emerge from different principles but share remarkably similar mathematical structures. The idea that our universe might exist within a black hole emerges from profound theoretical work in the holographic principle and black hole thermodynamics. These fields explore how information behaves at reality's most fundamental levels, revealing connections between seemingly separate phenomena that suggest deep underlying unity in nature's design. Consider the holographic principle, one of theoretical physics' most revolutionary concepts. This principle suggests that all information contained within a volume of space can be represented on its boundary surface, much like how a holographic recording stores complex three-dimensional images on a flat surface. When you look at a hologram, what appears to be a three-dimensional object is actually encoded as interference patterns on flat film. Applied to black holes, this principle suggests that everything falling into a black hole, every particle, every photon, every piece of information, might be encoded as information on the two-dimensional surface of the event horizon itself, creating a cosmic library written in quantum mechanics' fundamental language. The black hole's interior might actually be a projection of information stored on its boundary. This concept emerged from physicists like Gerard 't Hooft and Leonard Susskind, who were resolving fundamental paradoxes in black hole physics. Stephen Hawking had shown that black holes emit thermal radiation and slowly evaporate, but this created a puzzle. If information falling into a black hole is destroyed when the black hole evaporates, it would violate quantum mechanics' fundamental principle that information is always conserved. The holographic principle offered a solution by suggesting information isn't destroyed but stored on the boundary in forms we don't yet understand. If our universe exists within a black hole, then everything we experience, every star, planet, and particle, every thought you're thinking right now, might be encoded as information on that cosmic event horizon's surface. From our perspective inside, this information unfolds as the rich three-dimensional reality we inhabit, complete with time's flow, nature's forces, and the intricate dance of matter and energy creating galaxies, stars, and ultimately life itself. This perspective offers elegant explanations for puzzling cosmic features. The cosmic microwave background radiation, that faint Big Bang afterglow filling all space with gentle warmth just 2.7 degrees above absolute zero, could represent the thermal radiation that black holes emit according to Hawking's calculations. Every photon of this ancient light might be the cosmic equivalent of Hawking radiation emanating from our cosmic event horizon. The accelerating expansion of our universe, driven by mysterious dark energy, might reflect the natural growth of our black hole's event horizon as it continues accumulating matter and energy. Black holes grow larger as they consume more mass, and their horizons expand accordingly. If we exist within such a cosmic black hole, the expansion we observe might simply be the natural consequence of our cosmic home continuing to grow and evolve. Even time's arrow, that mysterious phenomenon distinguishing past from future, finds natural explanation in this model. Within a black hole, spacetime's extreme curvature creates what physicists call a preferred foliation, a natural way of organizing space and time that points inexorably toward the central singularity. This geometric structure could give rise to our experience of temporal flow from past to future. In thermodynamics' quiet and elegant mathematics, scientists discovered that black holes possess temperature, entropy, and other thermodynamic properties typically associated with ordinary matter, revealing unexpected connection between gravity, quantum mechanics, and information theory that have revolutionized our understanding of reality's fundamental nature. This remarkable revelation, pioneered by a theoretical physicist like Stephen Hawking and Jacob Bekenstein in the 1970s, revealed that black holes aren't perfectly black objects that only absorb without giving anything back, but instead slowly radiate energy back to the surrounding universe through quantum mechanical processes occurring near their event horizons. The temperature of a black hole follows a precise mathematical relationship that is inversely related to its mass. The more massive the black hole, the cooler its temperature becomes, following principles that emerge from the quantum mechanical processes occurring in the intense gravitational fields near the event horizon. This relationship emerges from the extraordinary quantum mechanical processes that occur where space-time is most severely curved, where the intense gravitational field creates particle-antiparticle pairs from the quantum vacuum through a process that transforms the virtual particles constantly appearing and disappearing in empty space into real particles that can be detected and measured. Near a black hole's event horizon, the quantum vacuum, that seething foam of virtual particles that quantum mechanics tells us fills all of seemingly empty space, becomes dramatically affected by the extreme gravitational field. Particle-antiparticle pairs that would normally appear and quickly annihilate each other are instead separated by the intense gravitational gradient, with one member of the pair falling into the black hole while the other escapes to infinity, creating what we observe as Hawking radiation. This process requires the black hole to lose energy and mass over time, causing it to slowly evaporate while emitting thermal radiation, whose temperature depends precisely on the black hole's mass. For a stellar mass black hole with several times the mass of our Sun, this temperature would be incredibly tiny, less than a billionth of a degree above absolute zero, far colder than the cosmic microwave background radiation that currently fills our universe. Such black holes are actually gaining mass faster than they lose it through Hawking radiation, because the background temperature of the universe is still higher than their Hawking temperature, meaning they absorb more energy from their surroundings than they radiate away. But for a black hole with the mass of our observable universe, containing approximately 10^53 kilograms of matter and energy distributed across the vast cosmic structures we observe through our telescopes, this temperature would be roughly 2.7 degrees Kelvin, approximately 2.7 degrees above absolute zero, the coldest possible temperature in nature. Remarkably, this almost exactly matches the temperature of the cosmic microwave background radiation that we observe filling all of space with its gentle, uniform warmth. That faint afterglow of the Big Bang that represents the oldest light in the universe. This extraordinary connection suggests a profound unity between the thermal properties of our universe and those predicted for cosmic-scale black holes by the laws of quantum mechanics and general relativity. The gentle warmth of the cosmic background radiation, barely above the coldest possible temperature in nature, and detected by sensitive instruments as a faint glow coming from every direction in space, might actually be the Hawking radiation of the cosmic black hole in which we reside. Every photon of this ancient radiation, carrying information about the universe's earliest moments when it was much smaller, denser and hotter than today, might represent quantum processes occurring at our cosmic home's distant boundary. The entropy of such a cosmic black hole would be enormous beyond human imagination, proportional to the area of its event horizon measured in units of Planck length squared, which represents the smallest possible unit of area in nature according to quantum mechanics. This entropy, approximately 10^13 bits of information, represents the total amount of information that could be stored on the boundary of our universe, creating a cosmic library vast enough to encode every possible state of matter and energy within our observable cosmos, every possible arrangement of particles, every possible configuration of fields and forces across all of space and time. From this perspective, the increasing entropy of our universe, that inexorable march toward thermodynamic equilibrium that we observe in everything from melting ice cubes and mixing gases to the evolution of stars and the formation of black holes, might reflect the fundamental information processing occurring at our cosmic boundary. Each moment of time, each interaction between particles, each quantum measurement that collapses a probability wave into a definite outcome adds another entry to this vast cosmic database, contributing to the universe's growing catalogue of realized possibilities and experienced states. Let us now turn our attention to the quantum realm, where the familiar rules of everyday experience give way to a strange and beautiful dance of probability, uncertainty, and interconnection that forms the foundation upon which all larger structures in the universe are built. In the microscopic world of atoms and elementary particles, reality becomes fundamentally probabilistic rather than deterministic, existing in multiple states simultaneously until the moment of observation or measurement collapses these ghostly possibilities into the definite outcomes that create our classical world of everyday experience. Picture yourself standing in a vast concert hall filled with billions upon billions of musicians each playing notes so soft and delicate they're barely audible individually, but together creating a symphony of unprecedented complexity and beauty that fills every corner of space with harmonious sound. The quantum field that permeates all of reality resembles such an orchestra, with virtual particles constantly appearing and disappearing, according to the rhythms and harmonies prescribed by the fundamental equations of quantum field theory, creating a cosmic performance that never ends and never repeats exactly the same pattern twice. These quantum fluctuations, occurring at scales trillions upon trillions of times smaller than an atom, might seem completely irrelevant to the grand structures of galaxies and cosmic evolution that we observe through our most powerful telescopes. But within our cosmic black hole, these microscopic variations become the seeds from which all larger structures grow, amplified by the extreme curvature of space-time and the long timescales of cosmic evolution into the macroscopic features that define our universe. The uncertainty principle of quantum mechanics ensures that even the most perfect vacuum is never truly empty, but instead filled with a constant fizzing of quantum activity that provides the raw material for cosmic evolution. During cosmic inflation, that brief but extraordinary period approximately 32 seconds after the Big Bang, when our universe expanded exponentially in size, growing by a factor of at least 10^26 in less than 10^30 seconds, these quantum fluctuations were stretched from subatomic scales to cosmic proportions through a process that seems almost magical in its implications. What began as microscopic uncertainties in the quantum field, existing at scales smaller than the wavelength of gamma rays, became the slight variations in density that eventually grew under the influence of gravity into galaxies, galaxy clusters, and the vast cosmic web of structure that fills our universe today. The holographic principle suggests these quantum processes might actually occur on our cosmic black hole's two-dimensional boundary, with three-dimensional space being a projection of information encoded on this distant surface. Every quantum interaction might represent information processing occurring at the cosmic horizon, billions of light years away. In geometry's gentle mathematics, we discover that space itself possesses rich, complex structure influencing every aspect of physical reality. Unlike the flat, unchanging stage space appears to be an everyday experience, the universe's true geometry is dynamic, curved, and intimately connected to matter and energy distribution within it. Imagine a vast, soft mattress stretching infinitely, perfectly smooth and flat. Now picture placing a massive bowling ball at the center, watching it create a deep depression curving the entire surface around it. This captures how mass and energy curve space-time according to Einstein's field equations, creating gravitational effects we observe throughout the cosmos. Within our cosmic black hole, this curvature takes on extraordinary properties. The immense mass contained within our universe curves space-time so dramatically that it closes back upon itself, creating a finite but boundaryless region of space. Like a two-dimensional ant walking on a three-dimensional sphere's surface, unaware its flat world curves through higher dimensions, we move through space that curves through dimensions we cannot directly perceive. This curvature has profound implications for how we understand distance, direction, and location's very meaning within our cosmic home. The shortest path between 2 points, known as a geodesic, follows spacetime's curved geometry rather than Euclidean straight lines. Light rays bend travelling through gravitational fields, and time itself runs at different rates in regions of different gravitational intensity. The cosmic web, that vast network of galaxy filaments separated by enormous voids characterizing our universe's large-scale structure, might represent space-time geometry's natural expression within our cosmic black hole. Just as soap films naturally form minimal surfaces when stretched between wireframes, matter and energy distribution in the universe might reflect optimal configuration for information flow within our curved cosmic space. Dark energy, that mysterious force causing space's accelerated expansion, finds natural explanation in this geometric framework. Rather than being strange new energy filling the vacuum, dark energy might simply represent our cosmic black hole's event horizon's natural tendency to grow larger as more matter and energy falls inward from surrounding space. Time within our cosmic black hole behaves in fascinating ways, with different regions experiencing moments flow at different rates. Near any black hole's event horizon, time dilation effects become pronounced. To an outside observer, time would appear to slow dramatically for anything approaching the boundary. But from our perspective within, we experience time flowing normally, each second feeling as it should. This creates a beautiful paradox. We might be experiencing billions of years of cosmic evolution that, from an external perspective, appears to unfold in mere moments. The entire history of our universe, from the Big Bang through first stars' formation, galaxies' birth, heavy elements' emergence, planets' formation, life's origin and consciousness evolution, might represent what an outside observer would see as brief gravitational collapse. Throughout the cosmos, four fundamental forces orchestrate the grand ballet of matter and energy, creating everything from atoms to galactic superclusters. Like musicians in a vast orchestra, these forces, gravity, electromagnetism, and the strong and weak nuclear forces, each contribute their unique voice to the cosmic symphony, playing for nearly 14 billion years. Gravity, paradoxically the weakest fundamental force, dominates on cosmic scales because of its universal attraction and unlimited range. Every particle attracts every other particle with gravitational force that, while incredibly weak between individual atoms, becomes overwhelming when dealing with enormous masses of planets, stars, and galaxies. Within our cosmic black hole, gravity serves as the cosmic conductor, organizing matter and energy into large-scale structures we observe. Electromagnetism governs interactions between electrically charged particles, binding electrons to atomic nuclei in quantum mechanical orbitals, creating the foundation for all chemical processes. The light streaming from distant stars, radio waves carrying information across space, warmth we feel from sunlight, all represent different frequencies of electromagnetic radiation propagating at the cosmic speed limit. The strong nuclear force, operating only at distances smaller than atomic nuclei, binds protons and neutrons together, creating periodic table elements through complex quark and gluon dances. In stellar cores, this force enables nuclear fusion, the process transforming hydrogen into helium and releasing energy powering stellar burning for billions of years. Every carbon atom in your body, every oxygen molecule you breathe, was forged in ancient stars' nuclear furnaces. The weak nuclear force involved in certain radioactive decay types plays crucial roles in stellar evolution and cosmic production of elements heavier than hydrogen and helium. Supernovae depend on weak force interactions to trigger catastrophic collapse and rebirth, scattering heavy elements throughout space. Within our cosmic black hole, these forces might be unified in ways we're beginning to understand. Grand unified theories suggest that at sufficiently high energies, electromagnetic, weak and strong forces merge into a single fundamental interaction. Some theories propose all four forces represent different manifestations of a single, underlying cosmic principle. One of our cosmic environment's most remarkable features is how extraordinary complexity emerges from relatively simple underlying principles. Like a master artist creating intricate masterpieces using few basic colours, the cosmos generates boundless diversity through fundamental forces, particles, and geometric relationships governed by elegant mathematical laws. This emergence follows patterns appearing throughout nature at every observation scale. In mathematics, simple iterative equations generate fractals of breathtaking beauty and infinite detail. In chemistry, the periodic table's elements combine to create millions of different molecules with unique properties. In biology, DNA's four-letter genetic alphabet writes instructions for all life's extraordinary diversity. Within our cosmic black hole, this emergence principle operates on the grandest possible scales, transforming the early universe's smooth, nearly uniform conditions into today's rich cosmic structure tapestry. From tiny initial fluctuations emerged galaxies spinning like cosmic pinwheels, stellar nurseries glowing with newborn sun's light, planetary systems where chemistry gives way to biology, and ultimately consciousness itself. The universe operates like a vast musical instrument with resonances and frequencies spanning scales from quantum vibrations to cosmic oscillations unfolding over billions of years. This cosmic music, inaudible to our ears but detectable through careful observation, reveals deep patterns connecting elementary particle behavior to galaxy cluster evolution. At smallest scales, quantum field theory describes particles as excitations in underlying fields, like musical notes representing vibrations in strings or air columns. These microscopic harmonics find echoes in astronomical phenomena. Planetary orbital periods often form simple numerical ratios, creating gravitational music played over millions of years with clockwork precision. The cosmic microwave background radiation carries imprints of acoustic waves that travelled through the early universe's hot, dense plasma, creating sound waves with wavelengths spanning hundreds of thousands of light years. When we map temperature variations in this ancient radiation, we're listening to echoes of the universe's first song, composed in our black hole environment's cosmic symphony hall. Even black holes contribute to this cosmic orchestra through gravitational wave emission, spacetime fabric ripples propagating at light speed. When two black holes spiral together and merge, they create gravitational waves stretching and squeezing spacetime as they pass, creating cosmic chirps detectable by instruments measuring laser beam length, changes smaller than a proton's 10,000th width. In quantum mechanics' strange and beautiful realm, reality takes on a fluid, probabilistic character that challenges our everyday intuitions about the nature of existence and the meaning of actuality itself. Rather than following a single, definite path from past to future like a train running on predetermined rails, quantum systems exist in what physicists call superposition states. ghostly combinations of all possible configurations existing simultaneously in a kind of quantum limbo until the moment of observation or measurement collapses these ethereal possibilities into the single concrete outcome that becomes part of our shared classical reality. Within our cosmic black hole, this quantum indeterminacy might play out on scales far larger than the microscopic realm, where we typically encounter it in carefully controlled laboratory experiments. The many worlds interpretation of quantum mechanics, developed by visionary physicists like Hugh Everett III and refined by thinkers like David Deutsch, suggests that rather than collapsing into single outcomes when observed, quantum superpositions might actually branch into parallel realities, each representing a different possible history for the universe, all coexisting within the same underlying quantum framework like infinite variations on a cosmic theme. Picture our cosmic black hole as containing not just one universe with one history unfolding through time, but countless parallel versions of reality, each slightly different from the others, all coexisting within the same curved space-time like overlapping waves on the surface of an infinite cosmic ocean. In one quantum branch, the asteroid that struck Earth 66 million years ago and ended the age of dinosaurs missed our planet entirely, passing harmlessly through space, and those magnificent creatures continued to evolve alongside early mammals, perhaps eventually developing their own forms of intelligence, technology, and philosophy. In another branch, the molecular processes that led to the origin of life on our planet took a completely different evolutionary path, creating entirely different forms of biology based on alternative biochemistry using silicon instead of carbon as the foundation for complex self-replicating molecules. In yet another quantum branch, the fundamental constants of physics took on slightly different values during the universe's formation, leading to cosmic evolution along entirely different pathways. Perhaps universes where stars burn more slowly and live for trillions of years, or where the forces binding atomic nuclei are stronger, allowing for the formation of elements heavier than anything in our periodic table. These parallel realities wouldn't exist in the separate spaces requiring some form of interdimensional travel to reach, but rather as different quantum branches of the same underlying cosmic wave function, different ways the universe explores its own infinite potential. From our perspective within one particular branch of this quantum multiverse, we experience a single consistent history unfolding through time, with each moment following logically from the previous one according to the laws of physics operating in our branch of reality. But the information processing capacity of our cosmic black hole might simultaneously encode all possible histories, creating a kind of quantum library of infinite scope and detail that contains every story the universe could possibly tell about itself, every path it could take through the space of possibilities, every choice it could make at each quantum decision point. This perspective offers a profound new way of understanding probability and possibility that transforms our relationship with uncertainty, choice, and the meaning of existence itself. Rather than representing our ignorance about future events or reflecting fundamental randomness in nature's operations, probabilities might actually reflect the relative likelihood of finding ourselves in different branches of the cosmic wave function as it evolves through time. Every quantum measurement, every moment of observation, every decision we make as conscious beings might represent a kind of navigation through this vast space of possibilities, unconsciously selecting which branch of reality we experience while all other branches continue to exist in parallel exploring their own unique pathways through the quantum landscape. Even our capacity for imagination and creativity might represent a kind of quantum sensing ability, allowing consciousness to glimpse possibilities that exist in neighbouring branches of the cosmic wave function. Every work of fiction we create, every theoretical possibility we consider in our scientific research, every what-if scenario we explore in our minds during quiet moments of contemplation might correspond to actual realities existing in parallel quantum branches of our cosmic home. The stories we tell, the dreams we dream during sleep, the futures we envision for ourselves and humanity, all of these might not be mere fantasies created by imagination, but rather glimpses of alternative realities that exist alongside our own, in the vast quantum structure encompassing all possibilities. As we prepare to conclude our gentle journey into one of the universe's most profound mysteries, let us pause to appreciate the deep comfort and wonder that emerges from contemplating our possible existence within a cosmic black hole. Whether or not our universe literally exists within such an exotic and extraordinary structure, the very fact that we can contemplate such possibilities with mathematical precision and scientific rigor reveals something beautiful about the power of human consciousness to transcend its apparent limitations and explore reality's deepest structures through the combined tools of mathematics, observation, intuition, and imagination. The black hole universe hypothesis offers us a vision of existence that is simultaneously humbling and profoundly elevating, reminding us of our intimate connection to the cosmos while revealing that we are not separate entities struggling against an indifferent and hostile universe, but rather integral participants in a vast, coherent system of information processing and self-discovery that encompasses everything we have ever known, could know, or might someday come to understand about the nature of reality itself. In this cosmic perspective, every moment of awareness becomes precious and meaningful, every flash of insight a contribution to universal understanding, every experience of beauty or love a note in the cosmic symphony, every act of creativity or compassion a participation in the universe's ongoing exploration of its own infinite possibilities. We become partners with the cosmos in the grand project of transforming potential into actuality, of bringing order from chaos, of developing consciousness from unconsciousness through the long, slow, magnificent process of cosmic evolution that began with the Big Bang and continues through our own lives and thoughts. The atoms that compose our bodies, the calcium in our bones and the iron in our blood, were forged in the nuclear furnaces of ancient stars that lived and died billions of years before our sun was born, making us literally children of the cosmos, inheriting the accumulated chemical wealth of countless stellar generations. We are made of star stuff, as Carl Sagan beautifully expressed, but more than that, we are the universe becoming conscious of itself, developing eyes to see its own beauty, minds to comprehend its own complexity, and hearts to feel love for its own infinite creativity and potential. Of the cosmos, inheriting the accumulated chemical wealth of countless stellar generations. The carbon in our muscles, calcium in our bones, iron in our blood, all were created in stellar cores under unimaginable temperature and pressure conditions, then scattered through space during supernova explosions to eventually become part of life's molecular machinery. This perspective offers profound comfort in times of difficulty or uncertainty. When we feel isolated or insignificant, we can remember that we are literally made of star stuff, that our thoughts participate in cosmic information processing that began with the Big Bang, and that our capacity for love, understanding, and creative expression represents the universe's own drive toward greater coherence, meaning, and beauty. Consider how this transforms our relationship with mortality itself. If we are information patterns within a cosmic black hole, then our existence participates in something far more enduring than individual biological lives. The memories we create, the love we share, the knowledge we contribute, all represent information patterns becoming part of the universe's growing understanding of itself. Nothing meaningful is ever truly lost. Everything becomes part of the vast, ongoing conversation between consciousness and cosmos defining our cosmic home. As our exploration draws to a gentle close, imagine yourself once again floating peacefully in space's vast, comfortable darkness. But now this darkness feels fundamentally different from when we began our journey together. Rather than seeming empty or cold, it feels filled with infinite possibility and connection, warm with consciousness exploring its own depths. You are not floating alone in an alien void, but rather resting peacefully within a cosmic system so vast and unified that it encompasses everything you have ever known or could know. The gentle hum of cosmic background radiation continues around you, but perhaps now you can recognize it as the soft thermal whisper of the cosmic black hole serving as your home, each photon carrying information from existence's quantum boundary itself. These ancient messengers, older than the oldest stars, carry messages written in the fundamental language of space, time, matter, and energy, telling cosmic evolution's story from the Big Bang's first moments to your present moment of peaceful floating. Your breathing slows and deepens as you float in this infinite cosmic embrace, feeling gravitational pull, not as a constraining force, but as space-time's gentle curvature holding all things in proper relationships, from smallest quantum fluctuations creating virtual particles to largest galactic superclusters stretching across hundreds of millions of light years. This curvature cradles you like the most comfortable bed imaginable, supporting you in perfect weightless comfort as you drift toward peaceful sleep. The question of whether we truly live within a black hole may never be definitively answered by science, but exploring such possibilities reveals something beautiful about the human spirit, our willingness to question deepest assumptions about reality, to follow mathematical insights wherever they lead, and to find meaning and beauty in even the most abstract cosmic possibilities. This capacity for wonder makes us partners with the universe in its own self-discovery process. As you drift towards sleep, carry with you this image of a universe that is not a cold mechanical system operating according to blind physical laws, but a warm, unified whole in which every part participates meaningfully in the cosmic dance of information, awareness, and discovery. You are not separate from this dance. You are the dance expressing itself through the unique pattern of matter, energy, and consciousness that you call yourself. Sleep well in your cosmic black hole, knowing that every dream you dream participates in the universe's ongoing exploration of what it means to exist, to be aware, and to wonder at being's extraordinary mystery itself. Space-time's gentle curve cradles you in perfect safety, and the vacuum's quantum fluctuations whisper lullabies older than the stars themselves, songs that have been playing since time's birth, carrying you gently into dreams where boundaries between self and cosmos dissolve into pure wonder and peaceful rest. Rest now, cosmic wanderer, in the universe's infinite embrace that is not only your home, but is, in the deepest sense, yourself. Let the cosmic microwave background radiation sing you to sleep with its ancient song, a lullaby playing for nearly 14 billion years, carrying you gently into dreams where space and time become fluid, where past and future merge into eternal present, and where every possibility exists simultaneously in cosmic consciousness's quantum foam. In the morning, when you wake from cosmic dreams, you will return to the familiar world of solid objects and linear time, but perhaps you will carry deeper understanding of your place in the grand cosmic story. You're made of star stuff, thinking star thoughts, experiencing the universe's own journey towards self-awareness through consciousness's miracle that emerged from billions of years of cosmic evolution. Sweet dreams, fellow traveller in the cosmic black hole we call home. May your sleep be filled with peace that comes from knowing your place in the vast, beautiful, unified system of reality, holding us all in its gentle gravitational embrace. And may you wake refreshed and wonder-filled, ready to continue participating in the greatest adventure of all, the universe coming to know itself through your eyes, your mind, and your endlessly curious spirit.